Okay, this video is the first video for chapter 5. Um, in chapter 5, and what we're going to start looking at now are heat gains. In chapter 5, we're dealing with base heat transfer, heat gains and heat losses to or from a space um, based on conduction and convection. Now, when we get into the next chapter, chapter 7, what we're covering is chapter 7, we're going to be looking at solar heat gains. But in this chapter, we're specifically focusing on convection and conduction. And the main part that we're going to be focusing on is convection and conduction based on wall construction. So you have walls and buildings, and the walls are constructed from numerous materials such as gypsum board and constructional studs, as well as insulation. And so we're going to be looking at thermal properties and coming up with effective thermal properties for them, for basically looking at resistance and how that resistance affects the heat transfer rate to those walls. But before we get into that, let's look quick at the equations that govern conduction and convection, namely Fourier's law and Newton's law of cooling. So Fourier's law is related to conduction. If you remember, it's going to be thermal conductivity times area multiplied by the temperature gradient. Again, where K is quantified as thermal conductivity, A is area, and dt dx is what's called the thermal gradient. Now, the thermal gradient can be approximated for our purposes as a change in temperature across a material divided by the thickness of that material. Now, the main chart that we're going to be using for conduction is table 5.1, and you can find that in chapter 5 starting on page 122 through page 128. Now on the right hand side here you have a little excerpt of what the table looks like. So if you can look at the left hand column here, you have description of the material. So we have different construction materials there. Some materials you have given thicknesses as well as densities. And then the last three columns give you the thermal conductivity, the thermal conductance, as well as specific heat. Now, if you remember, thermal conductivity in English units is, sorry, not English, but SI units is watts per meter Celsius. And in English units, that would be BTU per hour foot Rankine. Now, the ultimate goal of what you're trying to find is thermal resistance. And if you recall from heat transfer, in for conduction, the thermal resistance is the thickness of the material over the thermal conductivity, or 1 over the conductance. Now, these tables that we're looking at are not going to give you thermal resistance directly, but they do give you thickness, conductivity, and conductance, and you can kind of use those materials to extract and calculate what the thermal resistance is. You can go ahead to and recast Newton's law, I'm sorry, not Fourier's law, to quantify it in terms of conductance, or sorry, resistance or conductance. But basically, again, we're going to be using these tables to calculate resistance. So that's for conduction. If we move on to convection, convection is quantified according to Newton's law of cooling, which is the heat transfer coefficient times temperature multiplied by the change in temperature between the delta T between the surface and ambient. Again, where H is the convective heat transfer coefficient, and Ts is the surface temp, and Ts is the ambient temperature. As far as resistance for convection, that's equal to 1 over the heat transfer coefficient, or also conductance is equal to the heat transfer coefficient. And those values are found in table 5.2a. So let's go ahead and let's take a second and look at table 5.2a. So here you have a table that gives you a rough estimate of different heat transfer, convective heat transfer coefficients. So the first column, we have here the position of the surface relative to whether the air is still or moving. So if the air is still, you have the orientation of the surface, whether it's horizontal or not, and then the direction of heat flow from that surface. In regards to moving air, orientation is not important. It's just basically whether you have winter conditions or summer conditions. As far as the heat transfer coefficient is concerned, something else to take into account is emittance. If you remember in radiative heat transfer, the Q is calculated according to Stefan Boltzmann's law, right? Stefan Boltzmann's law states that the heat transfer, the radiative heat transfer is a function of the temperature difference to the fourth power, the difference between the temperature to the fourth power of the surface and the two surfaces that is exchanging radiation with. Usually, we would not associate too much convective heat transfer and radiative heat transfer, but in this case, this table goes ahead and separates out different heat transfer coefficients based on the emittance value. So this emittance value of the surface has an effect probably on the color, and the color has an effect on the emittance is what I meant to say, and the emittance has an effect on the convective heat transfer coefficient. So as long as you have the emittance for the surface, you can go to this column and you can figure out what the heat transfer coefficient is based on the surface orientation, whether it's still air or moving air, and you can get the heat transfer coefficient and also the thermal resistance. Now, looking at this, let's take a quick scenario here. Let's say that I have a simple wall made up of two materials, and I have outside air that is warmer than inside air, right? So I'd have heat transfer flowing this way, Q. If I were to quantify that, my Q, the heat traveling through, would first travel from the outside surface to the outside wall, right? So that would be governed by convective heat transfer. Remember, where delta T0 represents the temperature difference between the outside air and the outside surface. Then the heat would travel through the first layer of the wall, which that would be governed by heat conduction. Then the second layer of the wall, again by conduction. And then the final step would be the heat conduction through the inside surface to the inside air. So if I go ahead and I take this equation, recalling that conductive thermal resistance is the thickness of the material divided by thermal conductivity, and my convective resistance is 1 over H, I'll go ahead and I'm going to solve for each of my delta T's. So if I do that, I get Q over HA for delta T0. For delta T1, I get Q divided by KA divided by delta X. I get the same thing for delta T2. and delta T for the inside air, I would get Q over H1A, H inside A. So if I solve all those equations in terms of resistance, I would get the following. Q over A times the convective resistance for the outside. Delta T1 is Q over A times the conductive resistance going through layer 1 of the construction of the wall, then layer 2, and then the inside air. Now, if I take all of that, and what I want to do is solve for the temperature difference between the outside air and the inside air, I'll just basically sum up all those delta T's. And I'd get the following: Q over A times the addition of all those resistances, which basically helps me to derive how to calculate the effective thermal resistance of materials aligned in series, which simplifies to the following equation. My effective resistance for heat transfer flowing through materials excuse me, that are in series, I just sum them all up. But what if I have heat transfer in parallel, right? I have heat flowing this way, and I have heat transfer through two different materials, but both materials are lined up side by side, and heat transfer is going through both of them at the same time. Well, in that case, I'd have to compute my effective resistance according to the principle of my materials being lined parallel to heat flow. So I'd sum up the inverse of all the resistances of materials, take that number, and take the inverse again. So basically the challenge in this chapter, or what we're going to be looking at, is being able to look at wall constructions along with the convective resistances of the inside and outside air, align them up according to whether they're parallel or in series in regards to the heat transfer flow, and come up with effective thermal resistances. Okay, thank you. That ends this chapter, and we'll continue with example problems as we get into the following. Sorry, this concludes this video, and we'll continue the chapter by looking at example problems in the next video.